Our third question is on inclined planes. So the question is asking us to find how much force a box must be pushed up a ramp given certain quantities. So first we draw our diagram, we include our forces, and we label our coordinate system. We have a box on a ramp inclined at 30 degrees to the horizontal, which I've represented as theta. In this question we have forces acting in 2 dimensions, so we have the weight force directly down, the normal force perpendicular to the surface, the applied force F up the ramp, and the friction force opposing it down the ramp. If we think about our coordinate system, we can make our life quite a bit easier. So I'm going to choose the coordinate system as follows. So since now, by choosing such a coordinate system, we already have the x and y components for 3 of our 4 forces. The next thing to do is to find the x and y components for the remaining force. So I'll just remove the box and make it more like a free body diagram. We also then have the weight force in the y direction and the weight force in the x direction. The next step is to translate the question, so what we're looking for. We're asked for the force required to start the box moving. That means we're looking for the minimum force that will overcome the static friction, which means we're looking for the minimum force just above mu s times n. We're also asked for the force required to keep the box moving at a constant velocity. So that means we're looking for the applied force that's equal to the force due to the kinetic friction, which is mu k times the normal force. We're given mu s and mu k in the question, so what we really need to find is the normal force. To do that, we find the net force and we resolve our forces. So since this is a 2-dimensional problem, we will need to resolve our forces into the horizontal and vertical components, which we've already done in our diagram, so that should prove no problem. We're looking for the normal force, so really all we're interested in is the vertical components of the forces. We know that there's no vertical acceleration, so the net force in the y direction is 0. And we also know that net force is equal to the sum of the vertical forces, so that is the normal force plus the y component of the weight force. In solving this, we find that our normal force is equal to the y component of the weight force, which we don't know. So we'll look again at our diagram. And our weight force, we can see, is a right-angled triangle. So we can use trig to find the y component, but we don't have any of the angles. So we need to use geometry. So I'm redrawing the diagram again to make it easier to see. I've just shifted the starting point of my weight triangle to make it easier for me to do the geometry. I could just as easily have made the force lines in the diagram longer, and neither will affect the solution. So we're dealing with right-angled triangles, and we need an angle inside our weight triangle. So for example, this one. Looking at the triangle, the right-angled triangle that contains theta, we know that the yellow angle must be equal to 90 minus theta. On the other side, we have a right angle, so we know that our missing angle in our weight triangle must be equal to 180 minus 90 minus theta, which is equal to theta. So the y component of our weight is equal to w times cos theta, which is mg cos theta. Now for me is a good time to check what it is that we were actually trying to find, because I've probably got myself lost in the geometry. So what we wanted was the normal force, so that we could find the applied forces in A and B. So we have that our normal force was equal to the y component of the weight, which is w cos theta, and now we can substitute in that value to answer the question. And we find that the required forces in part A must be greater than mu s times w cos theta, and in part B must be equal to mu k times w times cos theta.